Today we're going to discuss a different subject, public key cryptography. The cryptography that we show until now is perfectly okay if you have changed the key. So now we have the problem of an insecure channel, and you want to use a block cipher key, so maybe a block cipher. It's okay if you want to use a block cipher by K. The insecure channel, you can say, okay, phi is the encryption. But what about the key? How can we send the key if we have an insecure channel? Or if you have a string cipher, it's the same. String cipher. For string cipher, you have the seed. And how can we transmit this? Okay. If we have a secure channel, we use it. But if we don't have it, we must create a secure channel using mathematics. Now we'll do a little bit of algebra, and that will be useful to show how we can do this. So some algebra will allow an insecure channel to become a secure channel. So we are considering F2 is the field of bits 0, 1. It has another name. Its name is also called Z2. And this name comes from the following fact. You can take any number, say 11, an integer, and you divide by 2. And you take the remainder. The remainder of division by 2 of 11 is 1. Now, if you take the remainder of the division by 8, it's 0. Now, if you divide by 2, you always get 0, 1. So the 2 are actually remainders of division. Of division by 2. In the same way, we can consider ZP, where P is a prime. Note that the operation on the remainders are the same as the operation that we do on F2. So when in F2 we say 1 plus 1 is 0, 1 corresponds to an odd number, odd. 1 corresponds to odd number. Odd plus odd is even. So if you sum a number with remainder 1 with another number with remainder 1, you'll get a number with remainder 0. So the same thing happens if P is a prime. So, for example, we can take 5 is a prime. Now, what are remainders? So we define Z5 as remainders of division by 5. What are the possible remainders? 0, 1, 2, 3, 4. What we do, we write the following. 11. If we divide 11 by 5, we get remainder 1. So what we do, we write 11 is congruent to 1 mod 5. Now, we can do operations here, and when we get a number which is bigger than 5, we just divide and take the remainder. So, for example, 4 times 3. 4 than 10 is 11, which is congruent to 2. Mod 5. So if it's obvious that we are working Z5, you can just write equal. So for example, 3 times 3 is 9, which is 4. So in Z5, 3 times 3 is 4. Now, what is the similarity between Z2 and Z5, or ZP? Well, so 1 plus 1 is 0, as you can say. You can say that 1 is the inverse of itself. So minus 1 is 1, because the sum is 0. Now if you take this is Z2. Now in Z5, 3 plus 2 is 0. So minus 3 is 2. Or if you prefer, 3 is minus 2. Okay, when we have this, in mathematics, we say that we have an additive group. So what is an additive group? An additive group is a set, you have an operation which is called a sum or addition, and for any two elements you get with this operation another element, and this group is also called a Boolean, because what happens is that this A plus B is equal to B plus A. So we have this operation which is commutative. Then we have a special element which is called 0. 0 means that A plus 0 is A for any element. Also here in Z5, 3 plus 0 is 3. And the same here, 1 plus 0 is 1. Then you can sum more things together, and the order doesn't matter. A plus B plus C is A plus B plus C. And we have this property also in Z2 and Z5. And finally, for any element there is an inverse. So for any A in G, there is minus A in G, such that A plus minus A is 0. And this we see it happen in Z5 and in Z2. So it's not obvious that 3 has an inverse in Z5, but it has. The inverse of 3 is 2, additive inverse, because 3 plus 2 is 0. So anytime we have a structure with these properties, we say that it's an additive group, an abelian additive group, but in additive group usually we consider abelian. So what we see is that so we see that ZP with the sum is an abelian group. Additive abelian group. Now we can consider multiplication also. What about multiplication? Okay, in Z2 we can remove the 0 and we get only 1. 1, you can do much with 1. 1 times 1 is 1. That's all you can do if you use multiplication. Now in Z5 it's less trivial. In Z5 you have that you can multiply, so 2 times 2 is 4, so we can multiply again. Then we can multiply in any order, 2 times 3 times 1 times, I don't know, 4 is equal to 2 times 4 times 3, the same. It's commutative, so it's commutative, we can multiply in any order, very good. There is a neutral element, 1, so for any A in Z5, A times 1 is A. And until now everything is obvious. Now there is something which is not obvious. The property about the inverse. What is the inverse in this case? So I'm trying to show that Z5 with multiplication is a group. In this case, a multiplicative group. Why it's a group? Well, for any group, what you need is the inverse. So I'm wondering, taking A in Z5, there is a number 1 over A in Z5, such that A times 1 over A is 1. Can we invert any element in 5, except 0, of course. So Z5 minus 0. Can we do that? Well, let's see. Can we find an inverse? Okay, what is the inverse of 1? When 1 times 1 is 1. So 1 is the inverse of itself. What about 2? 2 times 3 is 6. 6 modulo 5 is 1. So the inverse of 2 is 3. And the inverse of 3 is 2. Now what about 4? Well, 4 times 4 is 16, which is 1 modulo 5. So the inverse of 4 is 4. Note that the inverse we can also use, instead of write 1 over A, we can write A to minus 1. It's the same. Now about 4, actually we are using remainder, but minus 1 is congruent to 4 modulo 5. So if you divide minus 1 by 5 and you accept all the remainders between 0 and 4, you will get 4. So we know that minus 1 times minus 1 is 1. So 4 is like minus 1. That's why 4 is the inverse of itself, because 4 is minus 1. Because minus 1. Okay, this is true for Z5. This is also true for ZP, with P a prime. So we prove with Z5, and we claim that Zp minus 0 with the multiplication is a group, a abelian group. So Zp we plus in a abelian group, not additive. Zp minus 0 in a abelian group, multiplicative. And then the two operations linked. We have that A times B plus C is equal to AB plus AC. This we know. You can easily check. So if you have a set which is a group with respect to the sum, minus 0 is a group with respect to multiplication, and the two operations linked, then you have exactly defined a field. So I'm giving you a formal definition of a field. The group with operation, it's a group with respect to one abelian group with respect to the other except 0, and the two operations linked. One last thing, in Z5, we have interesting behavior. You take 2 in Z5 and you consider its powers. You have 2 squared is 4, 2 cubed is 3, 2 4 is 1. So all powers of 2 between 4 and 1, all powers of 2 form all non-zero element of Z5. This behavior is very similar to what happens with a primitive polynomial. In fact, in a field, more generally in a field, F, if there is an element in F such that all its powers are all the non-zero elements, in 1 and the cardinality of F minus 1, then this element is called a primitive element. So all its powers generate over the field except 0.